Oh, we we are in chapter 3. We will be examining circuit theory. What we have done already in this chapter was terminology explanation, all the terms that we will be using in this chapter. And circuit theory, we introduced the axioms of circuit theory, Kirchhoff current law equations and Kirchhoff voltage law equations, which are at the same time axioms, Kirchhoff's axioms, and also the axioms of circuit theory. Now what we are going to do next, how we are going to apply these axioms to the mathematical model of a circuit analysis. So that's that frame that we are going to examine today, right now. Not today, of course. This is a basic analysis method. Why we call it basic analysis method? Because we will be introducing some other methods which is simpler than this method later on. That's why that's the beginning. We use the basic analysis method. From time to time it might be called classical methods. Different names could be given to this method, but it is the most general one. So we already said that we've got, in order to have a mathematical model for the analysis of a circuit, we've got to write a set of equations which are independent set of equations, of which number of equations should be equal to the number of unknowns. That means the coefficient matrix, which is normally shown by X, shown here, that A matrix is going to be a square matrix. A determinant of this, if the number of equations are independent, then this A matrix inverse exists. Otherwise there is no inverse. So if the inverse exists, that means you can find all the elements, current and voltages as a unique solution. Therefore, we are saying the mathematical model must have equal. Mathematical model is going to be a linear algebraic equations, and these equations should be independent equations, and this number of unknowns and the independent equations should be equal to each other. In this case, there is a unique solution. So that's why the what are the independent equations? Let's examine to start this independent equations. If any the number of elements and d is the number of nodes, these are directly related with the circuit topology. Independent current voltage law equations is NE minus ND plus 1. So independent equations that we can write, Kirchhoff voltage law equations, is going to be this NE minus ND plus 1. Independent current law equations is ND minus 1. As we know, the one of the node is a dependent node. The current equation written for this dependent node is going to be a dependent equation. This node is called reference or the ground. So we are not going to write Kirchhoff current law equations for this ground. Number of definition relation for each element, one definition relation, then the number of definition relation for the elements is NE. So when add those up, you're going to end up with 2NE. 2NE is going to be the number of independent equations that we're going to write, and our unknowns are also 2NE. Why is that? We've got NE elements, and unknowns are the currents and voltages of these elements. So for each element there are 2 unknowns, NE element, 2NE unknowns. So the number of equations is the same as number of unknowns. The result, the solution that we're going to find by solving this equation is going to be a unique solution, and this is the solution that we are looking for the analysis of a given circuit. So in this area here, we can go into details. We will explain what is dependent equation is, mathematical information for you. Dependent equation. Assume that there are two or more equations. Assume that two or more equations are multiplied by constants and then added. New found equation is called linearly dependent. Any solution found for the independent equations are also the solution for dependent equations. Result: it is possible to find many dependent equations from the independent ones, but there is no use of these dependent equations. Therefore, independent equations are required. Let's examine it by an example. So there's two equations here, and these are independent equations, and the solution for these equations is x equal 5, y equal 2. If you multiply equation 1 with 1 and second equation by 5, so you're going to multiply this with 1, both sides, and 5 with this, and add those up, you're going to end up with this equation, 6x plus 4y equal to 38. So this equation here, which we found from those equations multiplying the first one with 1, the second one with 5, we found a new equation. This equation is a dependent equation now. This is dependent equation. Now what we are saying is this. The solution that you found from the independent ones, which is x5, y2 here, is also the solution for this equation. So that means when you introduce dependent equations, there is no use of it, because every dependent equation is going to have the same solution. Therefore, we need independent equations. Now we go back to the next frame. A bit explanation for the two any equations to any unknowns. Number of independent Kirchhoff-voltage law equation is equal to NE minus ND plus 1. We already said that. How we are going to find this equation? The next explanation is this. Kirchhoff-voltage law equations written for the meshes are independent. So that means we already defined what mesh is. Mesh is a special loop. If we write the Kirchhoff-voltage law equations for these meshes, then these equations are going to be independent. So there is no proof here, but there is no proof given here, which is not inside this course. But it's possible to prove that the number of independent equations is NE minus ND plus 1. What is said here, we are saying these equations are the ones which were written for the meshes. So I know how I am going to write independent Kirchhoff-voltage law equations. I'm going to write these equations for the meshes. One of the Kirchhoff current law equations is dependent on its. Let's come to the other axiom equations. The number of independent Kirchhoff current law equations is ND minus 1. In the previous frame, I just explained why one of the node is dependent, that is ground. We are not going to write any equation for this. So for the other nodes, we are going to write Kirchhoff current law equations, and these equations are independent. So this is I just said one of the Kirchhoff current law equations is dependent, and it is called as reference node or ground. Definition relation for each element is independent, and there are any equations for them. There are any equations for them. Any element, so any equations, definition relations. So when you add them up, total to any independent equations and unknowns to any unknowns could be written. That results in a unique solution. So this conclusion is quite clear that if the elements are the ones that we have seen, that means dependent sources, resistors included, any circuit is called a resistive circuit. The mathematical model of this resistive circuit is linear algebraic equations which are found as explained here. That means write the Kirchhoff voltage law equations for the meshes. Choose one of the nodes as a reference or ground and write Kirchhoff current law equations for the other nodes. These equations, the number of equations that you're going to write, Kirchhoff current law equation is going to be ND minus 1. And write the NE definition relations. So that's the mathematical model. Let's come to the next step. Give an example and what we said here, repeat it on the example. Now here we've got a circuit. This circuit has NE equals 7 elements. So that means the unknowns are 14. And number of nodes 1, 2, 3, 4, 5. We have chosen this as ground or reference node, so we're not going to write for this node any current equation. And this circuit has got resistors and has got one dependent source. This dependent source is a current controlled, because of this current controlled voltage source. Why it is voltage source? Because this dependent source has the diamond form dependent and the voltage reference is given. This blue current reference is put in by me. So in the original circuit it is not there. In the original circuit I've got voltage reference. Because of this voltage reference, this is a current controlled voltage, dependent voltage source, current controlled voltage source, of which voltage is equal 8 times IC. That means this voltage is controlled by this 5 ohm resistor's current. Now, how many equations that we are going to write is known, isn't it? Because unknowns 14, so 14 equations I am going to write. From these 14 equations, 4 of them is Kirchhoff current law equations. Why is that? As we said, we are going to write Kirchhoff current law equations for the nodes, not for the ground. So for these 4 nodes, I am going to write Kirchhoff current law equations. Let's write that. So the original circuit given to us is not in this form. What is added to this, I mark the nodes 1, 2, 3, 4, and also I put these current references to these elements. You see, all these blue ones has been put later on, and these meshes are also been marked afterwards. This mesh is not normally marked as it is done here. In the original circuit this is not there. So these mesh ones, these red ones, are the meshes, not loops. These are the special loops. In Turkish we call this, them göz. Now we said we are going to write 4 Kirchhoff current law equations for the nodes. For the first node it says y1 plus y2 is equal to 0. Why both of them has got plus sign in front of them? Because those 2 references are coming out of the node. That's why both have got plus. Just in parentheses to inform you that this reference here, blue reference for the independent voltage source, must be chosen like that. For the other ones there is no any rule. You could choose randomly the other blue ones, but except this dependent source as well. So what I am saying, this 5 current references could be chosen as you like. But this current here for the independent voltage source cannot be chosen randomly, because we've got this voltage reference for this element is given with the circuit. So we have to choose the current reference according to passive sign convention. That means current reference is going to start from the plus sign, goes to negative sign according to passive sign convention. Similarly, the voltage reference of this dependent voltage source is already been given. the current reference should be chosen according to passive sign convention. So that was in parentheses what was available, what we have added to this circuit. For the second node, there are 3 elements connected to the second node, and IC and I3 is coming out of the node, so sign of those two is positive. And the third current coming to the second node is coming to the towards the node, that's why the sign is going to be negative, so minus I2. Third node, we've got 3 elements connected to it, and I4 and I5, they are coming out of the node, therefore the signs are plus, and the IC current is negative because it comes towards the node 3, minus IC comes in. The last node 4, dependent source current, that is ICCVS, sign is positive because this current is coming out of the node. The other current is coming towards the node, that's why it is minus 5. So we wrote 4 Kirchhoff current law equations. This is what we expected. Independent voltage law equations, we're going to write independent voltage law equations for the meshes. We've got 3 meshes, so and this is in the order: first mesh, second mesh, third mesh. The first mesh is this one, and we've got in this mesh we've got 1, 2, 3 elements. We're going to add those elements voltages equal to 0. So how are we going to write these voltages? This current, this loop's current direction and this independent source current direction is opposite to each other. This one goes from left, from down to upwards. The other one from up to down. So the opposite. So it's going to be minus 20. So there's a mistake here. This should have been minus 20 that. And the second element here is 2 ohm resistor. 2 ohm resistor voltage is V2. Since the mesh direction is the same as this element current direction, the sign is plus V2. For this 10 ohm resistor current direction is the same as the mesh direction, therefore the sign of is plus. So addition of all these equal to 0. Just remind you, this is not 40, this should have been 20 because our independent source voltage is 20, not 40. Second mesh is, for the second mesh we're going to write this equation. So addition of the voltages 5 ohm, 20 ohm, 10 ohm is going to be equal to 0. What's going to be the sign of these voltages? If the mesh direction and element current direction is the same, plus. If it is opposite, minus. So it is written here. So this is another mistake here. I'm going to correct this. This is going to be not I4, V4 of course. Third mesh, we've got 3 elements. So V4 is this. Sign is negative because this mesh direction and I4 direction is opposite. For the fifth element, directions of the current directions are the same, so it is plus. This last one, the direction of this current and this red color is the same, so it's going to be plus current controlled voltage source voltage. So we wrote the independent Kirchhoff voltage law equations which are independent. There are 3 of them. So these are the definition relation. If you see the definition relation, we've got the resistor definition relation is V equal to R times I, so it is there. And independent voltage source voltage is known as 20 volts is the definition relation. And the definition relation for the dependent voltage source is current controlled voltage source voltage is equal to 8 times IC. It is written here. So the total number of equations that we wrote here is 14. 7 of them definition relation, 3 of them Kirchhoff voltage law equations for the meshes, 7 plus 3, 10, and current equations, 4 of them, 10 plus 4, 14, unknowns 14, 2 times the number of elements, equations 14, so there is a unique solution. So this is how we are writing these any equations, an example for that. So if we transfer these results now to a mathematical model, linear equations, so it's going to be in this form: Ix equal to B. X is the unknowns. These are all the elements, current and voltage is seen here. And in here we've got 3 Kirchhoff current law equations. It should have been Kirchhoff voltage law equations, that is. And these are the current equations, and these are the definition relations. So you see in this matrix, the dimension of this matrix is 14 times 14, and the numbers that we observe in this matrix, the entities, could be either zeros, plus 1 and minus 1s. These are the Kirchhoff current law equations and voltage law equations, related equations. The other equations are the definition relation related equations. In the definition relations, element parameters, that means the coefficients that we use in the definition of these elements, are going to be seen in these equations. So this is the form, that's the mathematical model of this circuit. So we are saying all this, since the inverse of this A matrix does exist. Why is that? Because these equations are independent equations. Then, since the inverse of these A matrix exists, A to the power minus y times B gives you x. That x are unknowns. So what we say, the last, so the solution is given in here, all the elements, current and voltage values. If you do the operations in here, you end up with this solution. So we can, the next step here is the Proteus simulation of this circuit. We said we do the analysis in different platforms. One of them is the mathematical platform. That is the theory. That is the circuit theory. And you're going to do it by hand. And similarly, we could do the simulation. That means do the analysis of the circuit by using the Proteus simulation program. This program will be used in our labs. Most probably you already use this. So this is how we are going to simulate this given circuit in this Proteus simulation. It shows you. So that is, you're going to draw that schematic in Proteus and put these props, voltage and current props, and find the results here. Whatever you found here should be the same as the mathematical solution. Another platform that we use for the analysis is the MATLAB. Once you write these equations, you can transfer this result to a MATLAB command and then find the results directly by using a program. You don't have to do it manually. So MATLAB application for this example is you can find it under the Chapter 3 tools, MATLAB applications. You could exactly find the same circuit and how to solve this circuit. That means how to transfer this mathematical model to a MATLAB command, and how we're going to find the results. It is explained there, so you can check this as well. So we finished this now. Let's see what we have done now. We said we examined the terminology that we are going to use. We explained the circuit theory that we will be using, Kirchhoff current law, voltage law equations. From those equations, we set up a mathematical model for any given resistive circuit. So, and the next video, we will be examining the conclusions that we found in this chapter. So that's the end of this chapter, end of this video. Let's close it.